Good morning, ladies and gentlemen. Let me introduce myself. My name is Letícia, and I would like to present the results of the research Learning over the Attentional Space with Mobile Robots. These are the contents that I'll talk about in my presentation. The advancement of technology has brought many benefits to robotics. As robotics tasks become more complex, an increasing number of sensors have been added to robots. These sensors collect different kinds of information on the environment all the time. However, this brings a disadvantage. The increase of information that is received and needs to be processed online overloads the robot's decision system. As humans, daily we receive a large quantity of information that comes from different sources too. And filtering this information is part of the attentional process present in our cognitive cycle. Inspired by the way humans construct knowledge through interaction with the world and the human cognitive cycle, scientists seek to reproduce the same with artificial creatures, resulting in the research area of cognitive robotics. In our work, we developed the bottom-up attentional pathway of one cognitive architecture, and with this, our robots learned over the attentional space instead of the sensory space. We use CONNEN as our cognitive architecture. The model provides an agent based on consciousness that performs computations over attention-directed schemes, significantly reducing the space of the model's input dimensions. It has both a top-down and a bottom-up attentional pathway. In this work, we will cover only the bottom-up component that comes from the stimuli that the environment promotes in the system. In order to implement CONNEN, use CST, that is a general toolkit for the construction of cognitive architectures. The CST architecture is codelet-oriented since all main cognitive functions are codelets or groups of codelets interacting together. Codelets are small pieces of code that run in parallel, each one responsible for a well-defined task. Memory objects are objects used by codelets to store and access data. Codelets interact with each other through memory objects. The experiments were performed in a simulated environment and you choose the VRAP simulator. Use the Pioneer P3DX robot as our reference robot architecture. To conduct the experiments proposed in this work, use the combination of sonars and laser sensors. Although both measure distance, we position them at different heights in the robot, thus capturing distinct data and having different ranges. Sonar ranges up to 1 meter and laser ranges up to 10 meters. This allows us to simulate intermodal perception, that is a combination of data from different sources. Pioneer P3DX is already equipped with 16 sonars, but we used only the 8 front sonar readings. The 2D laser scanner sensor was positioned in the top center of the robot body, which was able to obtain 180 readings at each cycle, referring to the data from the front of the robot. Also use the ground truth sensor to capture the real position of the attentive robot in the environment. The actuators are left and right wheels. We construct 2 feature maps that aim at detecting the saliences in their specific domain from data from multiple observation spaces, direction, and distance. In this experiment, the goal of the robot is to learn to detect and react to salience in the environment. So these are the models of CONNEN that we used. We extend the general attentional framework of CONNEN at CST to allow an agent running the bottom-up course of attention to learn how to improve its behavior. In CONNEN, the attentional cycle starts when the agent sensors receive information from the environment. The sensor data is captured by the sensorial codelets and stored in the respective memory objects at each cycle, and a limited quantity of them is stored in buffers forming the sensory memory. The next step is the construction of the feature maps through perceptual codelets and compose the combined feature map. This map is calculated by a weighted sum of the values in each feature map considering the weights presented in weights memory object. This combined feature map is multiplied with the attentional map to compute the salience map. Then the decision-making codelet updates the attentional map values and define the winner of that timestamp using the winner-takes-all approach, the salience map, and the inhibitor and excitator cycles of the bottom-up model. This process comprises the attentional codelets implemented. After knowing which the winner is, it is the output of decision-maker codelet. and the salience levels we can use to feed the learner codelet that implements an intelligent algorithm to learn what action the agent must take in every step. Finally, this action is passed on to the behavioral codelet, which fulfills each of their behavior. It sends the action instructions to the memory container, that is a dynamical subfunction architecture, that decides which action must be performed by the motor codelet and save the values in the motor memory. Finally, from the motor codelet, the agent updates and saves around and moves around the environment, restarting the cycle. Each experiment involving the attentional agent had 3 modes of execution, differing in the data used to calculate the states. They are mode salience, that uses the salience map to compute the states; mode sonar, the states are calculated using the sonar readings; and mode salience plus sonar, that the states are calculated using the salience map and the sonar readings. In this learning agent, key learning requires the specification of the associated Markov decision process in terms of actions, states, and rewards. The list of actions is directly related to the task the agent must learn to perform. The goal of the experiment 1 was to make the robot learn to explore more regions of the environment without crashing and without any influence of an attentional system. In the second experiment, we learned to go to the winner feature found by the attentional model, where Vt is the index of the winning feature in instant t. In the experiment 3, we change the second action to rotate in the opposite direction of Vt. Thus, the information of who the winner of the attentional focus is in each instant helps the agent to avoid going to the salience, as it can turn in the opposite direction. Now, speaking about rewards. The robot should not stay immobile in the environment for a long time. Therefore, the associated values for this action are known, that is the minimum. Furthermore, we do not want the robot to turn for a long time, so the cost associated with this action is intermediate. Finally, as the objective of the experiment is for the robot to explore more regions of the environment without crashing, the action of moving forward is the one that promotes the most significant movement of the robot in the environment, considering the space traveled. So, this action is associated with a higher score. These are some of our results. By observing the action turn away from winner, one can see that the trajectories using the salience and sonar are almost coincident, except by the number of actions, that is, on average, greater for the salience mode. When analyzing the action turning towards the winner, it can be seen that the robot turns frequently, which increases the numbers of actions, but it does not necessarily increase the spaces explored by the robot. Furthermore, it is possible to note from these images that the resulting trajectories are contrasting, which indicates that the robot indeed has learned either to go to or move away from salient elements, according to the experiment goals. Looking at the trajectories performed by the non-attentive robot, it can be observed that the agent showed almost a linear path with discrete curves. This can indicate that the robot learned to move forward and turn when it is indispensable, like to avoid an obstacle. Considering the average number of actions in all experiments, the salience map experiment offered the best results. It is important to remark that the decision-making learned over the salience map considers information from both laser and sonar readings once they were used to create the feature maps that were combined to detect salience. With this, it was possible to promote a state space reduction that, if not possible, would prevent us from using laser data in the same way that the sonar readings were applied. In this case, the proposed learned model was able to learn a better policy over a state space that is a 95% reduction of its original sensorial space. As conclusions, the reported experiments show that the attentional map, specifically the salience map, as input to a reinforcement learning algorithm, leads to results as close as those achieved when using the original sensorial space, but with a sensitive reduction on the search space. Indeed, the state space reduction promoted by the attentional system without information loss is crucial to the use of multiple or redundant sensors without impairing the system feasibility. One drawback happens when no salience is identified in the scene and the robot behavior is erratic. As feature works, it suggests taking the drawbacks of using the attentional space to include a top-down mechanism that would act in the absence of the salient stimuli. Another possibility of improvement is associating observations over the original sensory data described in higher levels of encoding to the attentional space to allow for more complex decisions. Also, you suggest exploring new features derived from vision and evaluating the importance of emotion and motivation in learning. The references will be provided if needed. We'd like to thank CAPS and IBM for the financial support, and thank you very much.